I welcome you once again. Uh, Now we have amongst us our next speaker. She is Sharmelee Thangjam. She is working as head of the department in EC department at UIT Chandigarh. She has a teaching experience of 12 years in UIT PU Chandigarh, and her research areas are signal processing, communication, and embedded system. She has guided a number of ME and MTech theses in the area of and she has also developed a research project named as Low Power DSP Lab under grant received from AICT. So I welcome you, ma'am, in this session. And now I hope that there should be a fruitful interaction of all with our expert. So over to you, ma'am.
Good morning to all the participants. So I'll be talking on embedded system design aspects. So I'll be starting with introduction, then we'll go on to the various aspects of embedded system design. So I'll be talking about the embedded system design aspects. Before we start with the actual embedded system design, let's see what is the definition of a system. So a system is a way of working, organizing, or performing one or many tasks according to a fixed set of rules, program, or plan. It is also an arrangement in which all units assemble and work together according to a program or a plan. Examples of systems are, for example, you have a time display system like a watch, an automatic cloth washing machine washing system. Some certain definitions of embedded systems according to different experts. Some of the definitions are: an embedded system is a system that has software embedded into a computer hardware, which makes a system dedicated for an application or a specific part of an application or a product or a part of a larger system. It is also one that has a dedicated purpose software embedded in a computer hardware. It is also a dedicated computer-based system for an application or product. It is an independent system or a part of a large system. It is the software is usually embedded into a ROM, that is a read-only memory, or a flash. It is also any device that includes a programmable computer but is not meant for a general purpose application. It is meant for a specific application. These are also electronic systems that contain a microprocessor or a microcontroller, but we do not think of them as computers. That is, the computer is hidden or embedded in the system. Now, for example, let's consider a general purpose computer. It has the following components like a microprocessor, a large memory comprising the following two kinds of memory. That is, you have your primary memory, you have your secondary memory. Then you have input units such as your keyboard, mouse, digitizer, scanner. Then you have your operating system. Then general purpose user interfaces and application software, mostly in the secondary memory. Now, when we talk about an embedded system, we've just seen what a general purpose computer looks like. When we talk about an embedded system, there are three main embedded components. The first thing is it embeds hardware to give computer-like functionalities. Certain hardware is embedded in the system. Then it embeds certain main application software, generally into the flash or the ROM, and the application software performs concurrently a number of tasks. And these tasks are all application specific. Then the third thing is it embeds a real-time operating system. Okay, so in case of an embedded system, we have what is known as your real-time operating system, which supervises the application software task running on the hardware and organizes the accesses to system resources according to priorities and timing constraints of tasks in the system. Now, what is this real-time operating system? Briefly, I think this will be taken up in the later lectures, but just to give you a brief overview. This real-time operating system, it enables execution of concurrent processes or threads or tasks that are running concurrently. It provides a mechanism to let the processor run each process as per the scheduling. Your processes are scheduled, so as per the scheduling, and do context switch between the various processes, threads, or task context switching. Then real-time operating system also sets the rules during execution of application process to enable finishing of a process within the assigned time interval and with the assigned priority. So you have different tasks with different time intervals and assigned priority. The real-time operating system manages all these tasks and processes. This we can skip this. Sophisticated embedded system characteristics, certain characteristics, that is, we have in an embedded system, we have dedicated functions, we have dedicated complex algorithm, because these are all application specific, it's not general purpose. Then you have dedicated graphical user interface and other interfaces for the application. Then you have these real-time operations. This operation defines the ways in which the system works, reacts to events and interrupts, schedules the system functioning in real time. That is, your processes are functioning in real time, and executes by following a plan to control the latencies and to meet the deadlines. Then you have multi-rate operations. Different operations may be taking place at different rates. Okay, different rates. For example, you can have audio, video, network data, or stream and events have different rates and time constraints to finish the associated processes. So multiple operations running at different rates. There are certain constraints of an embedded system design. When we design an embedded system, there are certain constraints which we do not face when we go in for a general purpose system design. So the first constraint is available system memory. How much is the memory available to you on chip? Then how much external memory that you require to put in. Then the available processor speed, depending upon your application, you see which processor is suitable for your particular application. Limited power dissipation when running the system continuously in cycles of the system start, wait for event, wake up, sleep, run, sleep, and stop. So power dissipation should be kept at the minimum. Then performance, constraints of performance, power, size, non-recurring design cost, manufacturing cost. So these are some of the constraints we face when we design embedded systems. So now that was a brief overview of embedded systems. Now let's come to the second part, in which we have a look at the different processors and embedded system for what type of an application you select a particular processor. Now before that, let's have a look at the hardware units in the embedded system. The hardware units, you have the power supply, reset and oscillator circuits. Then you have input devices, interfacing, driver circuits. You have your processor, timers, interrupt controller, program memory and a data memory. Serial communication ports, parallel ports, output interfacing, driver circuits. Then you have system application specific circuits, which is for that particular application. Okay, now the processor consists of two main units, that is your program flow and the data path control unit. This part includes a fetch unit for fetching instructions from the memory. Then you have your execution unit, which includes the circuits for arithmetic and logical unit, and for instructions for program control task. Say, for example, your data transfer instructions, halt, interrupt, jump to another set of instructions, or call to another routine, or sleep or reset. Now, there are certain considerations that a system designer, an embedded system designer, has to take into consideration. The first one is when you're selecting a processor. That is, the processor instructions in the instruction set are all the instructions applicable for your particular application. Then the processor ability to solve complex algorithms used in meeting the deadlines for their processing. The maximum bits in the operand, that is whether in a single arithmetic or logical operation you have an 8-bit operand or a 16-bit or a 32-bit. Then the internal and external bus widths in the data part. An internal bus width, what is the width of the bus, whether it's a 8-bit bus or a 16-bit bus or a 32-bit bus. Then the clock frequency in megahertz and the processing speed. So the clock frequency, the processing speed you measure in millions of instructions per second or millions of floating point instructions per second. You have another benchmark. This is a dry stone. This is a benchmarking program for excuse me, measuring the processing performance. So these are various benchmarks through which you measure your processing speed and the clock frequency. So this is one thing that we have to keep in mind while designing an embedded system. Now, when we select these different processors meant for an embedded application, there are certain processors, microprocessors, microcontrollers, or a specific application processor that we can select. So the first one, you can either go in for a general purpose microprocessor like Intel 8086, PARC, or Motorola 68HC XXX family. Or you can go in for an embedded general purpose processor. This gives you fast context switching features like use of on-chip compilers. For example, an example of this embedded general purpose processor is your Intel Xscale. Okay, then the second type, you can have an application specific instruction set processor. Application specific instruction set processor, for example, you have microcontrollers from Intel, Motorola, Hitachi, Texas Instruments, Philips, and ARM. So you can have 8051, Philips 51XA, 51MX series, Motorola 68HC11, 68HC12, 68HC16. These are all application specific instruction set processor. Then some microcontrollers which are used in small scale embedded system. When you are a design on a small scale, you can either go in for an 8 or a 16-bit microcontroller like you have from the 8051 family or the PIC16FX series family, the Hitachi H8 family, the 68HC11 XX family. Okay, these are used in small scale embedded system. Then when we go in for a medium scale embedded system, we go in for 16-bit microcontroller like 8051MX family, PIC16F876, PIC18, Hitachi D64F2623FA, 68HC12XX, 68HC16XX. So these are used in medium scale embedded system design. Then in large scale embedded system, when you're going for a high-end system, we go in for 32-bit microcontrollers from the ARM family, the Cortex M3, Atmel 8091 series, the ST10 series, Philips LPC 2000 series, Texas Instruments C16, and TMS 470R1B1M, Samsung S3C44BOX. Then you have from the Hitachi SH7045F. So these are 32-bit microcontrollers that we use in large scale embedded system. Okay, this is not very visible. Okay. Then we can also go in for application specific instruction set processor. Application specific instruction set processor, like the second part. For the first one was your microcontrollers. The second one, you have your DSP processors, digital signal processors, or media processor, or an IO processor, or a network processor, or a domain specific processor. So these are all application specific instruction set processors. So you can, depending on your application, you can select any of these processors. So DSP processors, digital signal processing, meant for digital signal processing applications, like if you want to incorporate a MAC unit in your embedded system design, you go in for a DSP processor. So you can have from the Texas Instruments C28X family, C54, C64, or you can have from Analog Devices, the Shark or the Tiger Shark family of DSP processors, or Motorola 5600XX series. Then you can also go in for a media processor. If you have lots of uh, processing, video processing, speech processing, and so on, you can go in for a media processor like the one from Texas Instruments, TMS 320DM310, or Trimedia Philips media processor 1x00 series for processing, streaming, and data network, and image, video, and speech. Okay, so these media processors are meant for this image, video, speech type of application. Then you can go in for a general purpose processor or an application specific IP core. So in this, a general purpose processor or an application specific integrated processor is integrated into either an application specific integrated circuit or a VLSI circuit or an FPGA core integrated with the processor unit in a VLSI ASIC chip. Okay. Now, then you can also have an application specific system processor. So this is typically if you want to speed up your processor, fast processing you require, you go in for this application specific system processor. So typically in this type of processors, you have a set-top box processor or a MPEG video processor or a network application processor or a mobile application processor. So this is application specific. Then you can have a single purpose processor or an application specific instruction processor. Single purpose, which is meant only for a single purpose. For example, you have a floating point coprocessor which will work with your floating point operations, a CCD pixel coprocessor, an image codec in a digital camera, a graphic processor meant only for graphical applications, a speech processor, adaptive filtering processor, so on. Encryption engine, a decryption engine, a communication protocol stack processor, a Java accelerator. These are all application specific processors. Okay, this we can skip. Then you can have multi-core processors or multi-processor system using general purpose processor. That is, you have the system. So for example, you have multi-processor system for video conference system or embedded So here we had an overview of the hardware units, the processors which are used in your embedded system design application. Now, next we come to the hardware elements in an embedded system. Okay, so again we have seen the hardware elements, we had a look at the processors. Now let's come to the next one, that is the basic circuit elements in the system. The first element is your power source. So power source can be of two types. The power, the system own supply with separate supply rails for IOs, clock, basic processor, and memory and analog units, or you can have supply from a system to which the embedded system interfaces, for example, in a network card, or you can have charge pump concept used in system of little power needs. That is, when your power needs are very less, power requirements are less, you have charge pump concept where you have diodes and capacitors which charges through your wireless radiation and so on. For example, in your mouse or contactless smart card. So these are different types of power sources you can have. Then you need to manage the power dissipation also. Okay, so how do we do that? By clever real-time programming, by wait and stop instructions, by clever reduction of the clock rate during specific set of instructions. Specific set of instructions reduces your clock rate, optimizing your codes, and clever enabling and disabling of use of caches and cache blocks. Then the clock oscillator circuit and the clocking unit. So this is the second part. We had to look at a power source. Next is your clock oscillator circuit and the clocking unit. So here you have an appropriate clock oscillator circuit. Then you have real-time clock or a system clock and timers driving hardware and software. Then you have your reset circuit. Reset circuit is reset on power up. Then you have external and internal reset circuit. Then you can also have a reset on timeout of watchdog timer. Okay, so embedded system design, you'll be coming across watchdog timers. This type of timers are useful when you are when the system is stuck or hung. It gives certain timeout to the processor. So after that certain timeout, it resets your system. Okay. Then we come to the memory unit. There are different forms of system memory. You have the internal RAM, which is inside your microcontroller. I think it's not very visible. Then you have the RAM at the system on chip or the external RAM. Then you have internal caches at the microprocessor. Then you have external RAM chips. Then you can have flash, EEPROM, PROM, and ROM, which is external or internal. Then you have memory addresses at the system port. So these are the different types of memories. Now the function assigned to the ROM or EEPROM or flash, it stores the application program from where the processor fetches instruction code. So embedded system design, that is embedded system meant for a particular specific application. So this application program is stored in your ROM or EEPROM or flash. Then the ROM or EEPROM or flash, this is also used for storing codes for system booting, initializing, initial input data and strings. It is also used for storing codes for your real-time operating system. Then it also stores pointers, or that is the address of various service routines. You have your various service routines, your pointers, and that is stored in your ROM or EEPROM. Then what are the functions that are assigned to the internal, external, and the buffer RAM? So this type of memory, they store the variables during program run. When your program is running, the variables, it stores a stack. Okay, your stack keeps changing, stack pointer. Then it stores the input or output buffers, for example, for speech or image. The function that is assigned to the EEPROM or the flash, it stores the non-volatile results of processing. Then caches, what are the functions of the caches? It stores copies of the instructions, data and branch transfer instructions in advance from external memories. Okay. Then it stores temporarily the results in write-back caches during fast processing. Okay. So cache applications ke liye you have this cache memory. Then the next hardware element is your interrupt handler. Okay, we've seen the different types of memories and where these memories are used. We come to interrupt handler. So this you have this interrupt handling element for the external port interrupts, different types of interrupts. You have different types of interrupts in your microcontrollers for this embedded application. So you have external port interrupts, I/O interrupts, timer and real-time interrupts, software interrupts and exceptions. For different types of interrupts, you have this interrupt handler. Then you have a linker which will link your embedded system hardware. So this element will link and interface a circuit for the buses by using the appropriate multiplexers, decoders, demultiplexers, and it also interfaces with various system units. Then you have this I/O communication unit. Here you have your communication drivers like your network Ethernet or the serial driver to communicate with the host embedded system. So for this you have your serial buses and parallel buses, UART, I2, CAN, SM, I2C, SPI, CAN bus, different types of buses. SCSI parallel, fast SCSI, ultra. These are different types of serial and parallel buses. Okay. Then you have the media input output control element. Under this you have your keyboard or the keyboard I/O interface, the LCD display system interface, the ADC, analog to digital converter, single or multi-channel, the DAC, the GPIB interface, the pulse dialing element, modem, Bluetooth, and so on. So these are different I/O elements. Okay, so here we had to look at the various hardware elements. That is your basic circuit elements like power source, clock, reset, timers, memory, the glue circuit, etc. Okay, then next we've seen the hardware elements. Next we come to the software for embedding in the system. Okay, so you have here you have the ROM image, the programming languages, and the programming models. So let's have a look at what is this ROM image. Your final software, final stage software, that is you've written the code, the final that is intended for your specific application. This software, this is also called the ROM image. Okay, so now this system ROM memory, this will embed the software, the RTOS, the data, and the vector addresses. Okay, this has your final machine software. So this final machine software is where you have bytes at each address defined for creating the ROM image. Okay, then by changing this ROM image nothing but your program which contains this your system software, the RTOS, the data, and the vector addresses. So by changing this image, the same hardware platform works differently and can be used for entirely different applications or for new upgrades of the same system. That is, same hardware, if you change the ROM image, that is, if you change the program, the software, you can use it for different applications. Okay. Now you have a distinct ROM image in a distinct embedded system. A particular embedded system will have a distinct ROM image. The hardware elements between the distinct systems can be identical. You can have the same hardware, but it is a software that makes the system unique and distinct from each other and makes it intended for a particular application. Your ROM image can be compressed codes and data. So ROM image may alternatively be compressed software, for example, in a zip format, or it can be data, for example, the pictures in JPG or GIF format, along with the softwares required for decompression algorithm. Then next we come to the programming languages. Okay. First you have your machine language coding. Your coding can be in machine language. Here the programmer defines the addresses and the corresponding bytes or bits at each address. Now this type of coding is used in configuring some specific physical device or subsystem like your transceiver. The machine code based here machine code based coding is used. Then we have the assembly language coding. This is needed for invoking processor specific application. Okay, this is also required for understanding of the processor and the instruction set. This requires understanding of the processor and the instruction set. So if you have to do the coding in the assembly language, you need to know the type, the particular the processor that you're using and the instruction set of that processor. A program or a small specific part coded in the assembly language using an assembler. So that becomes your assembly language code. Now there are 3 steps that is required when using assembly language. You need your assembler, linker, locator before your final code is being burned into the ROM. Okay, so this is your flow diagram. You have the machine specific assembly language program through the assembler. Then it becomes the machine codes for the program at various addresses. From the library needed machine codes, you have this is given through the linker. This gives you the bytes for the link program. Then addresses are relocated. Through the loader, this is given to after relocating the addresses, this is given to as machine codes ready for loading at various address points. Now this is being burnt into the device ROM programmer using the burner. And finally, this is being embedded into the embedded system ROM memory. This is your conversion process from the assembly code to the ROM image. Then you can also have a high-level language programming language like your C or C++ or Visual C++ or Java. So these are the, when you going for this high-level language programming, these are the different program layers. You have preprocessor commands, you have main function, interrupt service routines, different tasks, the kernel and the scheduler, standard library, the functions including the network protocol, functions for sending stack and receiving stack. So these are the different layers. Okay. Then what is the function of the compiler? When you're going for high-level language programming, we need a compiler. Compiler it just generates an object file using linker and locator. The file for the ROM image is created for the targeted hardware. C++ and Java are the other languages used for software coding. Now, this is how we convert a high-level code, for example, a C program into a ROM image. So you have your C program functions. These are passed through the compiler, generates the machine codes in the object file. Then this is passed to the code optimizer. This generates the programming models. So programming models, how you write the programs using this language, high-level language, etc. So you have the sequential programming model, you have object-oriented programming model, and you also have control and data flow graphs, or the synchronous data flow graph, or the multi-thread graph model, the finite state machine for the data part, multi-threaded model, concurrent processing of processes or threads or tasks. So these are the finite state machine. Okay, for this we can go hardware description languages like your VHDL, Verilog, and so on. Okay. Okay, so we had a look at the different programming models. Now let's have a look at how at the different softwares for embedding in the system. So first we come to device drivers. What are device drivers? Now in an embedded system, there are a number of physical devices. You have physical devices like your keypad, your LCD display or the touch screen, memory stick, wireless networking device, parallel card, and so on. You have a number of physical devices. So in an embedded system, again, you have a number of virtual devices, not only physical device, a virtual device like pipe, file, RAM, disk, socket, and so on. So what is the function of this device driver? What does it do? This is a software for controlling or configuring, receiving, sending a byte or a stream of bytes from or to a device. Now, device driver can be a set of generic functions such as create, open, connect, listen, accept, read, write, close, delete, which are used by high-level programmers. So the function calls a specific software or an interrupt service routine which controls a device function or a device input or output. This also controls and functions by calling an interrupt service routine on hardware or software interrupt. When you have a hardware or software interrupt, it calls an interrupt service routine. It places appropriate bits at the control register or the word of your particular microcontroller. Then it sets up the status flag in the status register for interrupting, therefore running the interrupt service routine, resetting the status flag after interrupt service. Okay, next we come to the device manager. So device manager for the device and drivers. So you have your device management software. Usually it is a part of the operating system. This provides codes for detecting the presence of device For initializing, you detect the presence of device. Once the device presence is detected, you initialize or configure this device, and testing the device that are present. So you have this device management software. There's also in software asking you operating system and real time. So processes, tasks, or threads. Now, the system is composed of two or more concurrent processes that execute multitasking software, scheduling multiple tasks, processes, memory, device, ports, network, file system. Keep several
आ रही आने आनी चाहिए
your digital camera, robots, point of sale term for a robotic system, washing machine, digital panel for voltage, current, resistance, laser print. In a server, switch, bridge, hub, and gateway. Then in a distributed
Net.
systems, for example, embedded systems for video, interactive video, broadband, IPv6, internet, and other products. Okay, so these are the different applications of embedded systems. So everywhere we look, right from the smallest application to the most sophisticated. units, your digital and analog units. So you can embed a general purpose, can also be embedded on a VLSI chip. Application specific course, different course. This can also be embedded on the VLSI chip. Then we can embed a multiprocessor or a dual core using general purpose processors. For example, we can have speech signal compression and coding, a processor meant for this. Can also be chip. Accelerator will speed up your processing for a particular application. This will accelerate the execution of codes. For example, a floating point coprocessor. This will speed up your floating point operation. This accelerates the mathematical operations. This accelerator is also on a VLSI chip. Then we can embed single purpose processors which are meant for a single purpose. For example, for dialing, modulating, transmitting, demodulating and receiving. Then keypad interface and display interface handling, touch screen, message display and creation, SMS and MMS, protocol stack generation, pixel coprocessor and codec in a digital camera. So these are single purpose processors. This type of single purpose processors can also be embedded on the VLSI chip. So system on a chip is an embedded processor, general purpose or application specific core, or it can have single purpose processing cores or multiple processing cores, or it can have a network bus protocol core and encryption decryption function cores for FFT, fast Fourier transform, discrete cosine transform for signal processing applications, memories and so on. Then you can also have multiple standard source solution called IP cores or intellectual property. This can also be embedded. Then you can have programmable logic device and FPGA cores and other logic and analog units. What is this intellectual property, IP cores? This is a standard source solution for synthesizing a higher level component by configuring a core of the VLSI circuit or the FPGA core available as an intellectual property. So a higher level component, this is being configured as a core, and then you can as a core, an IP core. It can be either a core of the VLSI circuit or it can be an FPGA core. Then it is embedded onto the VLSI chip, so it becomes a system on a chip. Then you can also have high level components with gate level sophistication circuit much above the level of counters and registers. Now, designer or the designing company, this holds a copyright for the synthesized design of a higher level component for the gate level implementation of an IP. Okay, it holds the copyright, so it's not freely available. So one might have to pay royalty for every chip shipped. An embedded system may incorporate several IPs. So we can buy an IP core. You don't have to develop everything from scratch. Readily available IP core you can buy from a certain company, then you can embed it into your system on a chip. An IP may provide a design. Examples of IP cores. It can provide a design for adaptive filtering of a signal, the full design for implementing your HTTP protocol or a file transfer protocol, your USB port controller, Bluetooth, GPS interface, wireless interface, and so on. So you don't have to develop the code by yourself. Then what are these FPGA cores? that is your FPGA field programmable gate array. Now this consists of a large number of programmable gates on a VLSI chip. There is a set of gates in each FPGA cell, which is called a macro cell. Embedded system designed with a view of offering enhancing functionalities in future. Then FPGA core can be used in the circuits. Okay, if you want to upgrade or if you want to enhance the functionalities, then normally we can go in for an FPGA core. So in an FPGA core, each cell has several inputs and outputs, and all the cells are interconnected like an array or a matrix. You have programmable interconnects between the cells. So each connection is programmable through associated memory RAM in an FPGA programming tool. The concept is using FPGA core along with single or multiple processors. So I use an FPGA core along with a separate processor or multiple processors. Examples of FPGAs are Xilinx Spartan 3, Vertex. Okay, these are all examples of FPGAs. This is an example. So, for example, in FPGA, using FPGA, a single instruction, multiple Fourier transform and its inverse, DSP or Laplace transform and its inverse, compression or decompression, encrypting or deciphering, a specific pattern recognition. Okay, this all can be implemented using your FPGA, and you can configure an algorithm into the logic gates of the FPGA. These gates are programmable and interconnects are programmable. So you can program the gates and interconnects according to your requirements. You can configure some algorithm into the logic gates. So we've just seen the subunits in a system on a chip, the IPs, how it is embedded into VLSI chip, and the embedded FPGA cores. Okay. Next, we come to the design processes and the design metrics for an embedded system design. Okay. Now, when we start with the design, the first thing we do is abstraction. Okay, the abstraction. So what is this? Every problem you will be given with some design problem. Okay, so every problem component, each problem component is first abstracted. For example, display, picture, and text. So if your particular application requires you to design something related to displaying picture and text, the display, picture, and text is created as an abstract class. Then robotic system problem abstraction in terms of controls of motors and different degrees of freedom if you're using certain controlling of motors. Then application software abstracted as concurrently running multiple threads and interrupt service threads. Then you have this different program model that we have seen earlier, that is procedure oriented, object oriented, sequential processes, concurrent processes, and your state machine. So object oriented model may you have class, objects, interface, package. Okay, when you go in for C++. Then you have hardware and software architecture. So this is assumed to consist of multiple layers. Each architectural layer must be well understood before a design. So hardware architecture, software architecture, the layers, you should understand the layers. Okay, I think we can skip some of this. Modular design. Okay, let's come to the design metrics. When we design an embedded system design, there are certain design metrics that we have to keep in mind. These are very important. So what are some of these design metrics? Certain design metrics are your power dissipation, your performance, process deadlines, user interfaces, the size, engineering cost, manufacturing cost, flexibility, the prototype development time, the time to market system, user safety, maintenance. Now, A design process, you call a design process as a bottom to top design if it builds starting from the components. If you start at the component level, this design process is your bottom to top design. Now, you call a design process a top to down design if it first starts with abstraction of the process, and then after abstraction, the details are created. So, top to down design approach is most favored approach because you are not dealing with the nitty-gritties of the lower levels. Now, these are the activities for software design during the software development process. This is your one life cycle, your development process. The first step in the software development process is to model or analyze the requirements of the system. First, you check for the requirements of the system. Second thing you go in for is your design. Okay. Then here you talk about the data structure, the software architecture, the interface, and algorithms. This all are specified in the second stage. The third stage, once you know about the data structure, the software architecture, interface, and algorithm, you go in for the implementation of the design. Now, after your design is implemented, you go in for testing. That is, you test the internal logic and the external functions. Okay. So if somewhere your requirements are not met, then you go back, you start the process all over again. So when we go in for the top level to the bottom level in the design process, there are 5 levels of abstraction. Okay. The first thing is the requirements. What is the requirements? When you are being given with a system to design, they'll give you with the requirements. Then the specifications, the architecture, the components, and the system integration. So in the requirements, you should have complete clarity of the required purpose. What is the system meant for? What is the intended purpose of the system? The inputs, the outputs, the functioning, the design metrics, the validation requirements for the final development system specification, and consistency in the requirements. So specifications, you should have clear specification of the customer expectations from the product. If your customer is expecting something else and your end product is something else, okay, the requirements will not be fulfilled. So the specifications are required for hardware, for example, the peripherals, device processor, the memory specifications, etc., the data type, and the processing specifications. Then expected system behavior specification, the constraints of design, the expected life cycle specification of the product, okay, because life cycle, time to market, and so on. The process specification analyzed by making list of inputs on the events list, outputs on the events, processes activated on each event. Then the architecture, what type of architecture you're going in for, whether you're going in for the data flow graph model, the program model, software architecture layers, hardware architecture, interface design, how do you integrate the system. Okay. Skip this. Then your hardware components. Hardware components, that is your processor, ASIP, single purpose processor in the system. What are you going in for? Are you going in for a general purpose processor or a application specific or a single purpose processor? Then your memory requirements, okay, your memory RAM, ROM, internal, external flash, or the secondary memory. Then the peripherals and device, internal and external to the system, the ports and buses, the power source or the battery in the system. Where is your power source going to be from? So we had to look at the different design processes, models, design metrics, requirements, specifications, architecture, components, and system integration. Next, next we have a look at the challenges in embedded system design, optimizing the design metrics and formalism of the system design. Okay. The first thing that we need to optimize is the amount and the type of hardware needed. So here you optimize the microprocessor, ASIP, and single purpose processors in the system. That is, if you have selected a particular microprocessor or a microcontroller or a DSP processor, it should be optimized for that particular application. Then optimizing according to the performance, the power dissipation, cost, and other design metrics of the system. Then we optimize the hardware. You try to optimize the hardware, that is your memory, RAM, ROM, internal, external flash, or secondary memory in the system, excuse me, and the power source or the battery in the system. So for all this, when we optimize, we take into consideration the different design metrics. For example, power dissipation. We want to keep the power dissipation at a minimum. Then physical size. For example, if you're designing something which is portable, you want the size to be small. Okay? The number of gates, engineering, the prototype development, and the manufacturing cost. The manufacturing cost is high, then you will not have customers for your particular product. Then the prototype development time it takes for the prototype to be developed. If it takes a long time, then maybe some other competitor will come up with a alternate product in the market. Okay, so you'll be at the losing end. So prototype development time, manufacturing costs, these are all design metrics that you have to keep in mind. Then optimizing the participation. How do you optimize the participation? Normally embedded system design, normally we have portable applications. So we can optimize the participation by going in for these different methods, like your clock rate reduction, reduce the clock rate, operating voltage reduction, wait, stop, and cache disable instructions by clever real-time programming, that is using of wait and stop instruction and disabling or controlling certain units when not needed. This is another method of saving your power during program execution. Then disable use of certain structural units of the processor to reduce power dissipation. When certain structural units are not being used, okay, you disable those units so that you reduce the power dissipation. Then process deadlines. So this is again a challenge when we design an embedded system, that is meeting the deadline of all the processes in the system while keeping the memory, the power dissipation, the processor clock rate at the cost at the minimum is a challenge. Then flexibility and upgradability. When you're designing a product, the ability to offer different versions of the product for different requirements. Okay, for marketing and offering the product in advanced version later on, the upgradability. Okay, that is also a challenge. Then reliability. Designing reliable product by appropriate design and thorough testing. Your product should be properly tested, verified, and validated. So this is again validation, verification, testing is again a challenge. Testing, we perform the testing to find errors and to validate that the implemented software is as per the specifications and requirements to get the reliable product. Then verification, this refers to the activity to ensure that the specific functions are correctly implemented. Validation refers to an activity to ensure that the system that has been created is as per the requirements agreed upon at the analysis phase and to ensure its quality. Okay, then we can skip this. Okay, the formalism of steps. First, the requirements and specifications of the hardware and software. This has to be addressed first. Then you define the architectures of the hardware and software, what type of hardware architecture, what type of software architecture you require. Then coding and implementation as per the architecture. Then testing, validation, and verification. Once you have developed your product, the final thing is to test, validate, and verify your system. Okay. Okay. Then we come to the last part. That is, I'm going to take up an example of a design process. Take up just one example, that is your automatic chocolate vending machine. Okay, example of an embedded system. So this is a diagrammatic representation of an automatic chocolate vending machine. Okay, these are the various blocks, modules. You need a keypad for the user interface, a mechanical coin sorter, LCD display or touch screen for the user, a microcontroller based hardware, real-time operating system, software, USB wireless modem, chocolate and refunded coins collector. Okay, this is meant for the customer. So here you have a coin insertion slot. So when the customer wants a chocolate, he inserts a coin. So you need a slot for coin insertion, a keypad on top of the machine, then LCD display unit on top of the machine, LCD display where you can see the display. It displays the menus, the text entered into the automatic chocolate vending machine, the pictograms, welcome, thank you, and other messages, graphic interactions with the machine, and it displays your time and date. Then you have a delivery slot so that the child can collect the chocolate and coins if refunded. Then interconnection port so that the owner can know the status of the vending machine sales from remote. Your owner will be monitoring from a remote place. So you need an internet connection. Now the hardware units that are required, you need a microcontroller or an ASIC. Then you need a RAM for storing the temporary variables in stack. You need a ROM for application codes and real-time operating system codes for scheduling the task, okay, your different tasks. Coin is entered, then it will give you chocolate, then depending it will calculate the amount that is to be refunded, the amount will be refunded. So then you have a flash memory for storing the user preferences, contact data, user addresses, user date of birth, identification codes, answers of frequently asked questions, and so on. Then you have an interrupt and timer and interrupt controller, a TCP/IP port for remote control and for getting the status reports by the owner. Then you have this vending machine specific hardware, power supply. Then the software components, keypad input read. When you're typing in the keypad, those inputs should be read. The display, your graphical display, read coins, delivering your chocolate. The software will control this part. This TCP/IP stack processing, TCP/IP stack communication. Okay, so this is an example of a automatic chocolate vending machine. So these are the different hardwares and software that are being used. Okay, I think I have other examples, but I think we can wind up here. If you have any doubts or any questions, can I proceed? Okay, so that is all about embedded system design aspects. I've given you a brief introduction to embedded system design, different types of processors, different types of then the software that you use. Okay, then certain examples and what are the different design metrics that you have to keep in mind, the challenges that you have to keep in mind when you design a specific product. Okay, so that is all. If you have any questions, any doubts, clarifications, I'm open.
Talk about abstraction processes.
Hmm.
We have two types of abstraction. One is top to bottom
Hmm.
abstraction process, and one is bottom to top.
Hmm.
What are the challenges that are being faced from the bottom to top? Because usually we say like these are very trivial things that we were using bottom to top, and these are very simple in implementing bottom to top abstraction process. What are the challenges actually that we are switching from top to bottom?
Okay, top to bottom. When you go from bottom to top, from bottom to top, if your design is very complex, very big, complex design, then if you start from the bottom, it becomes very complex because you have to know each and everything. Okay, for example, I'm designing a digital system.
Take this example.
Hmm. Huh.
This
Okay,
case,
in this case, इसमें everything. If you're starting from the bottom, you have to know the interconnections, circuitry, सब कुछ आपको पता होना चाहिए. But if you're starting from the bottom, then we just divide it into these modules. ये modules है. Okay, I'm just talking about the behavior. We just know about the behavior of that particular product. Then these different modules can be developed by different persons. Okay, so a keypad for the user interface can be developed by somebody else. Mechanical coin sorter can be developed by something else. Okay, we don't start from the bottom. अगर bottom से शुरू करें, then
bottom that we should have
complete.
complete.
So if your system is very complex, we normally don't go in for the bottom to top. We start from the bottom where we just know about the behavior, the different modules, the functionalities only. Okay, then you have your different softwares which will work on these different modules, and it will create the bottom level.
So we start from the application level.
From the application level.
Good morning. Ma'am.
Morning.
Yeah, I'm from BCD Sirsa. This is Manish Mehta. So, this is the diagram for the ACEM machine.
Okay.
Can you correlate this diagram with the actual coding or actual hardware? Do you have any uh, representation or do you have any material so that we can actually understand about this diagram with the actual hardware?
Okay. I'm just talking about the different design aspects. I'm touching on the different aspects of embedded system design, and this is just an example. I don't have the actual hardware circuitry. I think you can go in for this when you go in for the later sessions. Later sessions where you can take up a case example.
Okay, okay, right.
Now I'm just briefly touching upon the various aspects of embedded system design. इसका entire layout I don't have right now.
Because if the application is there, only then we can better understand. I think so.
Yeah, that is there. But then this is just an introductory lecture.
Right, right.
Okay.
Ma'am, I'm Venu from PPS IT, ma'am.
Okay. Good morning.
Good morning, ma'am. Can you make me a bit clearer about multitasking and multiprocessing, ma'am? With an
Multi
example possible?
multitasking again. That is very in depth. That is again an entire different topics. Multitasking and multiprocessing.
Just with a
It's all
small.
concerned with the real-time operating system. So real-time operating system is again an entire session. So I'll need another one or two session for real-time operating system. But however, briefly, embedded system design, mein you have a number of tasks and processes that are occurring simultaneously. Okay. So the real-time operating system is manages the switching from one task to another, how to meet the deadlines of a one task, then switch on to other task, and so on. Scheduling and context switching of this task. Okay, these are being carried out by your real-time operating system. So again, real-time operating system, this is again an entire, I'll require an entire session for this.
And multiprocessing, ma'am, how does it differ?
Multiprocessing.
Yes.
Multitasking is when you have a number of tasks. Multiprocessing is again different processing. Suppose you're processing an image or you're processing a speech. Okay, you're processing speech. So different processes going on simultaneously.
Okay.
Okay.
Any interrelation between both multitasking and multiprocessing, ma'am?
Yes, it can be there. Your processes, again, inside your process, when you're running a process, maybe that process it has a different task associated with a particular process.
Thank you, ma'am.